Okay, so today we start our class with power flow analysis, the topic number 1, because this topic we have two topic. Number 1 is power flow. Number 2 is fault. So fault we have two. Number 1 is balanced faults. Number 2 is unbalanced. Okay, so this one is power flow. We will learn about the equations, the power flow equations, and then the techniques. Okay, number 1 technique is Gauss-Seidel. Number 2, Newton-Raphson. Number 3, fast decouple. Okay, we try to learn about Gauss-Seidel today. Before that, we need to know that before we can use or we can construct the equation for Gauss-Seidel technique, we need to know about the Bus Admittance Matrix. Okay. So the outline of this this topic, like I said previously. So Bus Admittance Matrix today, we try to finish until Gauss-Seidel by this week. Okay. And then once we get the power flow solution for Gauss-Seidel, we can calculate the line losses as well as the line flow. Next, Newton-Raphson and fast decouple. So as introduction, the power flow studies can be referred as a load flow. So don't be confused. Sometimes I will call load flow, sometimes I call power flow. It's a similar meaning. And it is backbone of power system analysis and design, meaning that if you want to do the fault, you need to do the load flow analysis first. If you want to do the loss minimization, you need to adopt or you need to use load flow also. And even though you need, if you want to calculate or if you want to study about the protection also, you need to do the load flow first. So that's why the load flow can be said as the backbone of power system. And normally it is referred to the steady state condition, meaning there is no fault happen. Okay, so that's why it's in terms of new steady state operation. Basically, what is the load flow? Basically, we want to know about the voltage, the value of the voltage, the currents, as well as the real and reactive power flows in this power networks under steady state, under set of load conditions. Basically, this is necessary for planning, operation, economic scheduling, and exchange of power between utilities. So that's why I said just now, we require to run the load flow for fault analysis, transient stabilities, and contingency studies, and many more. So this is this example of single line diagram. Suppose you have learned or you know the single line diagram, right? From EPS. So this is single line diagram. You have generators, you have bus bars, as well as you have loads. So we want to know the power flow from the generators to loads, as well as we can calculate the losses also. And we can determine the voltage at the bus, each bus. So that's why when the system is bigger, you cannot do load flow by hand calculation. Basically, for bus system also it's quite complicated to calculate the load flow. Okay, and then the simplest way to perform power flow calculation is by iteration. Okay, that's why it will require iterations, meaning that if you make mistake at the beginning of your calculation, so you will your solution will be wrong all the ways. So that's why this topic or this subject, the failure rate is quite high due to you make mistake at the first place. So if you the solution requires 3 or 4 pages, you need to calculate by handwriting. Why you make mistake at the beginning of your calculation, so it will wrong all the way. So there is no marks for your efforts. So you get 0. So that's why we need to create a bus admittance matrix Y bus for the power system. And then we make an initial estimate for the voltage at each bus, update the voltage estimate for each bus in system at one time based on the estimates for the voltages and the power flows at every other bus and the value of the bus admittance matrix. Next, you need to update the voltage, and normally the updated voltage is not correct, but usually closer to the correct answer. Okay, that's why your results supposed to be as close to the correct one. Okay, the process is repeated until solution has converged to the correct answer. If your solution is wrong, you do the calculation is wrong, you cannot get the right answer, your solution, we call it diverge. So meaning it's a wrong answer. Okay, if correct answer, your solution will converge. So let's take a look at how you construct the bus admittance matrix. So you have 4 buses. You have bus 1, bus 2, bus 3, and bus 4. This is the initial one. We just calculate how we want to construct the Y bus matrix from this system. Normally, you change all the impedance in per unit. That's why you need to learn in EPS, because for easy calculations, change to per unit on a common MVA base. So this way, kita punya this is the your Z. Okay, Z from 1 to 2. This one from 1 to 3. This one from 1 to 4, 4 to 3, 2 to 3. This is your impedance. So we need to change. We need to change. Okay, we need to change this Z into Y. So the equation is 1 over Z. So that is Yij. If you can see that your small letter Y, meaning that is a impedance at the particular line. Okay, meaning that you need to change from Z to Y. Okay, so how we can do? You have 1 2, 1 3, 1 4, and then 2 3, and 3 4. So this is the systems shown for this bus 4 bus system. Okay, so number 1. Okay, before that we have types of bus. There is bus 1 represent, we call it slack bus, or sometimes they call reference bus. Okay, bus 2 is PV bus. PV stands for the voltage control bus. Bus 3 is PQ bus, meaning this is the load bus. Okay, never mind, later I will explain again. Bus 1, because you have generator there, we call it, when the bus is attached to the generator, sometimes it can be treated as the PV bus or slack bus. Normally at the system, we have one slack bus and the rest is the PV bus. We call it PV bus or control generator bus. Why? Because we know the P, we know the V. That's why we call it PV bus. Bus 2 and bus 3 is we call PQ bus or load bus. Why? Because we know the P and we know the Q of the load. And this one is PV bus. We know the P, we don't know V. This one is slack bus. Okay, this is the value of the bus generator, bus type. And then we have transmission characteristics or transmission properties. From bus 1 to bus 2, the R is 0.03, the X is 0.05. And then if you remember, okay, we continue. Let's say if you remember your transmission line, you have learned about the transmission line parameter, right? So from bus I to bus J, this is your model. Okay, this is bus I, this is bus J. So this is sending end, this is receiving end, this is your Z. So you have lump of the admittance matrix, right? Your B, or sometimes we call it Y. So this one is Y over 2 or B over 2. So this 2 is your half B. We call it the lump admittance. So some system will have these properties. Okay, and then sometimes your transmission line you have a transformer setting, transformer tab. Okay, so that's why you have also the transformer tab setting. But for your class, normally we just consider this one don't have. But your project we consider the transformer setting, tab position. Okay, so from bus 1 to bus 2, this is your value. Okay, bus 1, bus 2, this is your Z. And then bus 1 to bus 3, this is the value. Bus 1, bus 3, bus 1, bus 4. Okay, so this is value for Z. So what you need to do is you need to change into Y admittance matrix. Y equals to 1 over Z in order to get the Y bus. Never mind, we'll look at this one later. So this is the example. Example for the 3 bus system. We have 4 bus system, 1, 2, 3, 4. But we ignore the R for the simplicity. So there's the activity is to change from Z to Y. Okay, so what we can do is you change everything into Y. Z10 represent 1, 2 because this is our ground. 1, 0 represent ground. Okay, so this one 2, 0, meaning that this one Z2, 0. This one Z10. So you need to change to Y20. This one Y10. That's why you get these things. Z10 you change to Y10. This one is small Y, not big Y. So we use this thing. Jangan tertukar sebab Z huruf kecil dengan huruf besar ni akan represent different things. Ni pun silap, ni bukan Y kecil lah. Bukan Y besar, Y kecil. So 1 over J1 is minus J1. In this one, in terms of per unit, this one Z12 is 0.4. So 1 divided by J 0.4, you get this value. Z13 0.2, so your y is 1 over j 0.2, you get minus 5, and minus 12.5. So as you can see here, because of we divide the imaginary, normally becoming the negative one. Okay, so that is your admittance at each transmission line. So this is the admittance diagrams, and then from this figure we can change to this figure to present in terms of y, everything in terms of y. Next, we want to apply the concept of nodal, or your circuit theory that you have learned in circuit analysis. So we want to construct Y bus, call it Y bus or admittance matrix. But before that, we look at each particular bus. So we look at bus 1, this is bus 1. What we can see here, that all the current inflows must be equal to the current outflow, right? Remember? Or you remember the Kirchhoff KCL? The current inflow to the node must be equal to the current outflow. Okay? Let's say you have I1, I2, and I3. So I equals to I1 plus I2 plus I3. Or I minus I1 minus I2 minus I3 equals to 0, right? So you look at the node. So in power system, normally when you look at the bus, we can represent this bus as a node, titik. So current masuk sama dengan current keluar. So you can see here at bus 1, I1 must be equal to current keluar. If you remember, if you use our well-known Ohm's law, your current I equals to what? Z apa? Okay. V equals to I Z, right? So your I equals to V over Z. And you remember that 1 over Z is what? 1 over Z is Y. So that's why to calculate this current, it is Y10 times V, and then Y12, this one 12 equals to V1. This one is represent the V1, this one V2 at this line. So V1 minus V2 times Y12, you get this current. Similar for this one, V1 minus V3 times Y13, you get this current. So this one at bus 1. Similar with the bus 2, this current equals to this current, and this current. So you get I2 Y20 times V2, because V2 represent here plus minus, and then Y12 similar, but now is your V2 minus V1, right? So V2 minus V1 times Y12, or Y21 lah. Y12 dengan Y21 sama kan? And then you have Y23 times V2 minus V3. Similar goes at the bus 3, but bus 3 now you don't have the current source. These two have current source because these two we have generator bus, right? We have generator here. That's why you have current source. This bus don't have any current source, meaning that it's a 0. Similar, this is Y23 to 3, V3 minus V2, and then Y13, V3 minus V1, and Y34, V3 minus V4. And then for bus 4 is 0 equals to only one connection, V4 minus V3 times Y23. So if you look at here, you can rearrange in terms of matrix. We rearrange all the equations. My suggestion, you need to do it by yourself. Kena try lah benda ni. You rearrange, buat pengembangan, Y1, 2 ni besarkan. You do the expansion. One, you do the expansion. You do the expansion, you get, and then you rearrange, you can come up with this value. So all the V1, it equals to Y10, Y12, Y13 summation. And then V2 is only required Y12 minus, and Y13, V3 is Y13. There is no V4 because there is no connection between bus 1 to bus 4. No connection, meaning that is 0. Similar for I2, you get this one is summation of related to the bus 2. And then there's no bus 4 or V4. And then for this equation, as you can see that we come up with all the bus 3 summation, but we have V4 because we have connection. There is a line between bus 3 and bus 4. Similar with the this fourth equation. So, but there is no bus bus 4 that related to bus 4. We have so we have these equations. So we can rearrange and we introduce you the name of the admittance, the bigger one. So Y11 represent of this one, represented by this one, meaning that all connected to the bus 1 use sum. Y22 similar, all connected to the bus 2. Y33 all connected to bus 3. And Y44 connected to bus 4. Bus 34 only. Okay, that's why you have Y34 only. And then the rest is, as you can see here, this is summation. Positive values. So also positive values. But for Y12, we call it, this one is we call diagonal. Apa maksud diagonal? Diagonal ni kalau matrix, you ada matrix 4x4. Yang ni diagonal. Satu line ni, diagonal. Yang lain tu kita panggil off diagonal. Why 4x4? Because we have 4 bus. Okay, the rumus, the rule of thumb here, because you have 4 bus, you will have 4x4 matrix. Let's say you have system 20 bus, so you need to have 20 times 20 matrix. So that's why if 20 bus, you cannot do by hand calculation. So this one you need to program, or you need to do software to calculate the load flow. This is for your project normally. Okay, this one, the off diagonal, 1, 2 is equal to Y21. It is represented by minus Y12. Yeah, negative Y12. And then Y3, 31 represented by negative Y13. So this one is off diagonal. Similar with the 2, 3, 3, 2. To this one 1, 2, right? Similar. This one 2, 3. Okay, is represented by minus Y1, Y23, and Y34 this one minus Y34. So this one we construct already we want to construct the Y bus matrix. So this one we rearrange back. So you get I3 and I0, we just name it I3 I0 because this is just a 0, right? because there is no current source. So you get this value. At the end of the day, in terms of matrix, we can construct using this thing. Okay, meaning that if you make expansion of this one, you can get this thing, this equation. So that's why I1 equals to this we call it Y bus, or we call it bus admittance matrix.